Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today I would like to talk about one of my favorite combinatorial objects, and I was just thinking whether actually the topic is really also something I like. So I really like partitions. So partitions are absolutely fabulous. So partitions are totally great. We all love them. Partitions, fantastic. But then I was thinking whether I like to count them. So that's what I'm going to talk about, how to count partitions. And I realized that, yeah, I probably should, because I like partitions so much that I kind of should be interested in counting them. But it turns out that counting them is like very difficult. So in some sense, I shouldn't be interested in counting them. So I decided to call the subtitle to count or not to count. So I really want to count, but I somehow can't count. So I avoid counting and do something different. And actually, it will be quite fun. So I hope you will enjoy. But let's get started with one of my favorite combinatorial objects, the good old partitions. So a partition is nothing else than you fix an integer, let's say 5, and you write it as a sum of natural numbers. Something like 3 plus 1 plus 1. And I will just illustrate that by putting 3 boxes for the number 3 and 1 and 1. And note that addition is commutative, so I don't care whether it's 3 plus 1 plus 1 or 1 plus 3 plus 1, just the numbers that appear. I could also write something like 5 is equal to 2 plus 2 plus 1, and then I would draw a diagram of the following form. I would put 2, I would put another 2 boxes, and I would put a little box 1, right? So I can draw those little diagrams. And they're sometimes called Young diagrams, Ferris diagrams, partition diagrams. They come under various names. But essentially, I want to count those diagrams. And here's a very nice picture in the background, what I want to count. So here, all diagrams for 1. How many partitions of 1 are there? Well, I can just draw a box. And then the next, all diagrams for 2. So I can draw this box and I can draw this box. So this would be, in my convention, 1 plus 1. And of course, 2 is 1 plus 1, and this would just be 2. That's a little bit of a boring partition, but that one is allowed. And then you can continue, and you will see, well, that the number grows very fast. Right? So I'm really interested in, well, those numbers. So I should be interested in counting them, and this is a really classical problem. So Euler studied those, for example, already, and just count the number of p, the number p of n, the number of partitions of n. So here we'll start with p of 1 is 1, P of 2 is 2, P of 3 is 3, P of 4 is 5, P of 5 is 1, 2, 3, 4, 5, 6, 7. So it goes like this, and then it continues and grows very fast. And you kind of want to know, well, can you write down a nice formula for the number of partitions? Right? The number of partitioning integers into sums. Well, that's something we do all the time. It turns out, by the way, that these numbers appear everywhere and partitions appear everywhere. So everyone who likes combinatorics eventually will see those things. So if you really want to count those numbers. And it sounds like a quite innocent question. There should be some rule of doing this, just kind of dividing integers into other integers. It's just addition. There should be something we can do. And it turns out that this is like very, very delicate and not so easy to do. So let's go through some results. So the first count I know is kind of very strange and essentially due to Euler. It's related to pentagons. Counting partitions and pentagons. And when I learned this, I was like really surprised. What do an integer partitions have to do with pentagons? Like by pentagons, integer partitions? And I still don't have a really good answer, except that it actually works. So you can write the number of partitions as recursively, right? So Pn is Pn minus 1 plus Pn minus 2 plus Pn minus Pn minus 5 minus Pn minus 7 and so on. And there's a closed formula, which I'm going to explain in a second. Right? This is a recursive computation. And if it ever hits a negative number, it's 0 by definition. So you can kind of recursively compute those numbers. And what shows up here is, well, okay, it looks all good, but what are those numbers here? The 1, the 2, the 5, the 7, and they're called the pentagon numbers, and they arise as follows. It's absolutely absurd. Again, it's completely mysterious why the pentagon shows up. So here is my little pentagon, as you can see, and I can divide the pentagon into an upper part and the lower part, and because the pentagon is always kind of an odd thing, it will never come out evenly. And I count the numbers in the upper part as this is 5, not 7, it's 5. And I count the parts in the lower part is 2. And whatever I get as a sequence, so here the first one is 1, 1, 2, 5. Then here is a 7 and a 12. Whatever comes out in the sequence, so 0 is the first one if you want, and then 1, 2, 5, 7, 12, 15, 22. These are the numbers I stick in here. It's very mysterious counting formula. It's absolutely fabulous. So pentagon numbers, dividing pentagons into halves is related to integer partitions in such a crazy way. It's just absolutely fantastic. There's a sign, but let's ignore the sign. It's not so difficult. Anyway, so this formula solves our problem, right? It computes partition numbers. Well, it's absolutely fabulous, as I said, but I have a slight problem with this. So it's recursive. It's not really a closed formula, right? It expresses P1000 in a large sum of other P's. So I need to know essentially all of the other P's before I can compute P1000. So that's not really what I was looking for. Beautiful formula, no doubt. Pentagons and integers, integer partitions, fantastic, but not really explicit. So this is not really counting. It's kind of a pseudo count, right? To count or not to count. This is not really counting. At least in my opinion, whatever counting is. Let's ignore the question what counting is. Let's just call this not counting. Okay, and then there's another formula, which is, it fits up the whole slide, don't worry. I will explain the main ingredients. It's actually pretty beautiful. So you can write it down as a generating function. A nice closed function. It's actually a really simple function. It's just this product over the 1 over x to the k. You just take an infinite product, and don't worry whether it converges or not. We are algebraists here. We don't care about convergence. It's just an abstract symbol, and it's an infinite product which you can just write down like explicitly like here. And then you kind of collect coefficients of that infinite product, and what you will see are exactly the partition numbers, right? So you can expand this as a sequence of x to the n's, just by expanding it, essentially doing a Taylor expansion, and you will see the partition numbers turning up as coefficients. And this thing is called a generating function. Absolutely fascinating thing. So you can put all partition numbers for all n, Pn for all n are contained in one formula, right? That should count as a counting formula, right? Right? Turns out that I still don't believe that this is a counting formula. The problem is that I still need to expand my very efficient and absolutely fabulous, by the way, again, a very efficient way to write down all of these numbers. I still need to expand them to get a specific number. And that's, again, not what I would count an explicit formula. Again, very fantastic, but not really explicit. Yeah, so that's a bit disappointing from my end here so far. Well, not really, right? We have seen two pretty cool ways of computing something. Here is very surprising. The Pentagon one is just bonkers. I mean, where does the Pentagon come from? Well, if you have a good answer, just put it in the comments. I really would love to know. Of course, you can just prove it if you call that's where the Pentagon comes from. But maybe a nicer answer, I would really love to know. But anyway. And this one here is, you have a really nice function. It's 1 over 1 minus x to the k. It's not so terribly difficult. You just expand all of these. Here's the first expansion, here's the second expansion, and so on. Multiply them, collect coefficients. Very efficient way of doing it. But still, it's not really counting. The same problem as before. We want to really count, but we somehow can't really count. We only get a reasonably unexplicit formula. Actually, beautiful unexplicit formula. And here's another beautifully unexplicit formula. It's slightly differently. Instead of counting the number explicitly to say, oh, it's 15,012. That's probably not a partition number. I just threw it in. 15,012. You compute it asymptotically. So that gives you a closed formula, a fantastically beautiful one. So x makes an appearance, and pi makes an appearance. A square root makes an appearance. What a fantastic formula. But you lose the precision. So asymptotically really just means the ratio goes to 1. So here's an example of something asymptotic. So the zigzag curve asymptotically becomes a line. but they're not the same. And you're doing the same here. So you're not really counting this number, but you have a nice asymptotic formula, which is essentially perfect for n very, very large. And I say it again, contains e and pi and square roots. Who doesn't like that? I hope you do. Anyway, so here's our little formula again. And if I list them, here you can see that this formula, so I list the ratio. Eventually the ratio will convert to 1, but it takes a while. And it's in the 30th step, it's still quite off by a bit. So it's 90% correct. So this is still somewhat not really counting. We get a closed formula, the one I wanted, and it's a beautiful one, but it's not really counting. It's just counting asymptotically. It counts the ratio. It counts the difference. So asymptotically, you can kind of, if you're interested in how big, roughly how big p a million is, this formula will do the job for you. But it will be off by quite a bit. So it's still not doing the count, right? To count or not to count. And it's really off. So, but asymptotics are usually off by a lot. So it says that the ratio converts, but it doesn't say anything about the difference. And the difference indeed gets arbitrarily large. So here I list again the 31, which was 90% correct. Here I list it as a difference, and it's different. They're always different by 500. So I don't get the number p of n. I get the number p of n plus 500 in this case, roughly 500. So although the asymptotic formula is fantastic, it's absolutely great. I say it again, there's a pi, there's a square root, and there's an e. Fantastic, thumbs up. And it does a really good job for large n. It does only a really good job for the ratio. So it's still not really counting. Fantastic formula, but we still don't get Pn because the difference somewhat gets arbitrarily large. Anyway, and I don't know any better answers. So that formula is kind of my favorite counting formulas for the partition numbers. There are several more. So if you have anything you want to share, just put it in the comments. I would like to see it. But this one was my favorite, and it's still not really counting. So it turns out that this kind of innocent looking problem, just count integer partitions, is quite difficult to solve if you're really up for kind of an explicit counting formula. Anyway, I hope you enjoyed this video, and I also hope to see you next time.